circularly slotted ultra wideband antenna followed by an elliptical UWB antenna. First of all, after installation of this is CST 2021 software, after installation, if you click on that one, I'm going for a new design, new window. So go new and recent. There you have new template is there. This is new project from template pane. These are the recent files where I have opened or designed. And there are different modules and tools are available in CST software like 3D simulation, circuits and systems, PCBs, packages, antenna maggers, filter design, CST chip interface, PEST 3D, Spark 3D, system simulator, IDEM, Opera. Now, we're focused on a planar ultra wideband antenna design, so that click on new template. Then a window will be opened as CST Studio Shoot. Yes. Here, create project template. That create project template is mentioned. Choose an application area and then select one of the workflows. There are different types of workflows are possible to design or to use this computer simulation technology software. Microwaves and RF are optical, and then EDA, electronics, EMC, EMI, particle dynamics, statics, and low frequency. Because we are going for high frequency, that is microwave frequency, the antenna typically operated in terms of gigahertz, because ultra wideband antenna is to be operated from 3.1 to 10.6 gigahertz, so that we go for microwaves, high frequency waves. So click on that. Then on right side of it, you have various modules are displayed. One is antennas, circuit components, radar cross section, biomedical exposure, SAR, optical applications, periodic structures. So because I'm going to design antenna, click on antennas, then click on next. It will open a create project template. So in that you have to select one of the workflow. So either waveguide, horn type of antenna designing, or cone type of antenna, planar type, wire type, phased array, unit cell, mobile device up 6 gigahertz for phones and wearable applications, 5 millimeter wave, reflector, dielectric resonator, RFID. So in this case, my concentration is to design a patch antenna, microstrip patch antenna for ultra wideband application. So I'm going to choose a planar type of antenna. So in this discussion, in this hands-on experience, I focused only on planar type of antennas for the purpose of ultra wideband application. So that I select a planar type, click on next. So here the recommended solvers for the selected workflow, time domain, frequency domain, multi-layer are there. So we need to get both time domain and frequency domain. So time domain for wideband or multi-band antennas, frequency domain for resonant antennas, and multi-layer. We are going to use zero thickness thick metals, like in the case of characteristic mode analysis of antennas, we are going to use multi-layer. So right now I'm going to design wideband antenna, so that move to time domain solver, click on next. Immediately in the next template, it is asking about dimensions. So what dimensions we need to provide for the designed antenna, either in terms of meters, centimeters, millimeters, micrometers, up to here available. So I'm going to design the antenna in terms of millimeters, so that select dimensions in terms of millimeter, and UWB is in terms of gigahertz of frequency range, so that the frequency is selected to be gigahertz. Then time, nanoseconds, and remaining parameters These are important here, first three. Then click on next. So in this window, it is asking about choose the minimum value of frequency and maximum value of the frequency you need to design the antenna. So there you have to specify the minimum value and maximum value of frequencies for which you need to develop an antenna. So because I'm focused on 3.1 to 10.6 gigahertz, I'd like to give you a band of frequencies 2 to 12, and then there are monitors are there, E field, H field, far field, power flow, power loss, depending upon application. Then you can make use for all these to be checked, or 1 or 2 or 3 are to be checked, it is depending. So for biomedical applications, we required SAR value also. In such a case, we required power loss. So in the case of ordinary planar antennas, it is required E field, H field, and far field. My recommendation is don't go for H field and far field more than E field for the first time when you are going to optimization of an antenna. Because if you choose all the fields monitors have been checked here, it took more amount of time for the simulation. So we are focused on, first of all, whether we have to got S11 up to our required level or not, so that minus 10 dB level or not, so that we need to check E field. So in this design, I would like to go for H field and far field, because for the designed antenna already optimization process have been completed. So that in this case, I'm going to choose the monitors E field, H field, and far field. So then click on next. So this is the review of what we have done in the previous steps. So please review your choice and click finish to create the template. So here I have applied solver is time domain. Units are in terms of millimeters dimension. Frequency is in terms of gigahertz. Time nanoseconds. Frequency minimum value 2 giga, max 12 gigahertz. And the monitors I have taken in this case are E field, H field, far field. And because this is starting frequency and ending frequency, defaultly the monitors takes place at the center frequency also. It should be calculated the monitor values, E field value, H field value, and far field. So next, click on finish. Now it will take you to the design window of computer simulation technology software, where we need to design our antenna. So this is the portion. This is the portion where we have to design our antenna. And we can view this portion in different views. Say here, the views are there. Perspective view, front view, back view, left view of antenna, right, top, bottom. Simply if you are going to press key 5, it will show you front. And if you are going to press on 3, it will show you the back structure of the antenna. So whenever it is open, this is completely the antenna designed area where we need to design our antenna. And in the home, there is a navigation tree is there. As I said to you, the main advantage of CST software for the beginners is all the results have been navigated in this tree structure. So here the components have been what we are placed, the substrate, patch structure, ground structure, etc. have been included here, and then all the one-dimensional results have been placed in this structure and in this pane, and two-dimensional, three-dimensional results have been available here for fields, tables, and plots. In the case of MIMO antenna, we got envelope correlation coefficient, diversity gain, etc. So now this is home window. In this window, all the previous discussed units, and here setup solver is there. We need to again observe what type of solver you need to go for the designed antenna, either time domain, frequency, again mode, integral, etc. start simulation. Optimizer is there. So here you can provide optimization for the designed antenna parameters. Say if I'm going to take feed width is 3, we are going to alter the 3 value to 3.1 or 3 like 2.9 etc. In such a case, we have to define one variable for the optimization process for feed width or patch length or width for all the dimensions. And then there is a mesh view. Calculator is also provided here. This is about home window. Coming to modeling. So in the case of modeling, this is most important because the antenna structure is to be designed in this modeling pane itself. So here you have a brick is there for designing of rectangular square type of structures. You need to click on brick, and then you have sphere is there, cone, torus. Here you have cylinder type of structure, elliptical type of cylinder structures are there available there. And you have aperture TLM mesh only. Then to combine all these components, you have extrudes are there. Then some wires. You have to rotate the face, and you can also perform some operations on various number of antennas. Say if you are going to take multiple input and multiple output antennas, MIMO antenna. If suppose 2 antenna elements are there, so to transform them from one location to another location or to apart from separation distance, and also to perform some mathematical operations, addition, subtraction, intersection operations in between the defined structures, we are having a Boolean type of operation there. And you can perform bend of the defined structure also. In the case of wireless body area network, the bending of structure, say 10 degrees or 30 degrees, depending upon body shape, it is to be required. There you can make use these bending tools. And this is the peak phase curves are there. Peak phase is very most important while you are going to applying a waveguide port. And there you have local working coordinate system is there, local WCS. So the local working coordinate system is consisting of UVW components, whereas the axis is coincide with UVW or coincide with XYZ respectively. So XYZ are global coordinates and UVW are local coordinates. For convenience of clear view of structure, I would like to eliminate that global coordinates. And this is the bounding box, which is already set, defaultly set by CST itself. And if you want, you have to eliminate in the view for the purpose of clear view of designed antenna. Come back once again the modeling pane. So if you want to remove this portion also, I click on local working coordinate system. Then you have the next one, simulation. So again, in the starting, if you forgot to apply the frequency values, again you need to apply the minimum value or maximum value of frequency. Each and every time you should not go for creation of project template. Choose the minimum frequency and maximum frequency depending upon your application. Once again, in the simulation. And also there is a waveguide port is there. This is the port window I have shown in the PPT that I had presented in the previous case. You need to provide some dimensions like X minimum, X maximum, Y minimum, Y maximum, Z minimum, Z maximum to the waveguide port you have applied. Then discrete port is available. Field monitor. In this field monitor again, as I had shown in the previous case while creating the project template, either you have to choose an E field, H field, and surface current, far field. All those monitors are available. If you want to go for selection of a particular field monitor, check it, click on OK, and run or simulate the corresponding design. So defaultly it is showing E field. Click on OK. Then you have setup solver is there, because we have not applied any waveguide port till now. So it shows like this. So otherwise it can be opened one window, and there we have a start command is there. We have to click on that start to run our simulated design. Then again, peak phase is most important for the purpose of applying waveguide port, as I had discussed. And coming to post processing. So initially, while we are going to select the field monitors like E field, H field, far field, after simulation of all these three, you will get some one-dimensional results, two-dimensional results, and far field results. But we don't get the gain curve and envelope correlation coefficient curve, etc. To get that, we need to go for post processing. In post processing, you have result templates is there. In that result templates, whatever the parameter you need according to your designed antenna, say for example, if it is ultra wideband antenna, go for far field and antenna properties. Then in the below of it, you have far field result. Then a window will be opened for far field result, what parameters it is providing, like 3 dB bandwidth, angular 3 dB bandwidth, directivity, front to back ratio, gain, maximum electric field, maximum gain. This is important for us. The maximum gain over frequency. There you have, if it is a MIMO antenna, MIMO diversity gain over frequency, MIMO envelope correlation coefficient, multiplexing efficiency, etc. All these are available depending upon your required design. You can go for selection of a particular parameter and then click on OK, and then you can go for evaluate, which will give you that particular graphical representation of the antenna maximum gain over frequency. After you can give evaluation, click on evaluation. And then you have view section is there. This is for only just a view of all the results. You have to check the, you have to change the Y and X view. Either you have to zoom it or concise it. And you have working plane is there. Maybe if you click it, it shows a white plane. If you are clicking it like that, you can zoom the structure. All those are available here. You can hide a particular component which is designed here. Choose that component and hide, and show those components once again. For that purpose, it is to be used. Now, I would like to design the antenna where I had shown in the PPT, that is rectangular microstrip patch antenna. So this is the rectangular microstrip patch antenna, which is used for ultra wideband application. And I want to design this structure on hands-on in simulation right now, by using simulation software right now. So here, this is the red color one I have shown here, which is representing patch structure. Once again, I am just reminding, this is patch structure. Yellow color one is substrate, and on bottom side, a green color for representing in a different color. I have represented with the green color, and it is ground structure. And so to design this one, I would like to already optimized all the values, so that I would like to explain what to be taken to design of substrate, and how to design microstrip line feed, and design of rectangular patch, and how to obtain the notched structure of the rectangular patch, and how to design defective ground structure, and how to apply waveguide port to microstrip line feed, and then how to simulate it, and how to observe the results like S11, VSWR, impedance, radiation efficiency, surface currents, radiation patterns, gain, etc. in that result pane. And then I'm going to show you, for the purpose of time domain analysis, by placing the same antenna has been redesigned for the second structure. Those two antennas have been separated in side-by-side configuration and face-to-face configuration in time, for the purpose of time domain analysis, to get group delay, isolation, and phase. As I had discussed in the PPT, for ultra wideband antennas, we need to get a flat group delay whose group delay variations are less than 1 nanosecond, and isolation value is less than -30 dB. So first of all, I would like to design that single ultra wideband antenna design. So start our design. I would like to start the design. So go to modeling. There you have brick is there. So I would like to discuss slowly because it took some time because I have explained in online mode. It took some time to appear on the screen. So I took one brick to click on that brick. Then you have a window will be open there. So what is solid one in this case is I'm going to design first of all substrate. So I give a proper name reflecting the antenna design, the component structure. So I'm giving the name is substrate. And what is x minimum, x maximum. So these are the values where you need to give as in terms of variables like because x representing always width and y representing length of the patch you have designed. So here you have to give variable like the US substrate is to be symmetric with respect to this origin around x-axis and y-axis. So minus WS by 2 plus WS by 2. And similarly, for length of the substrate, I'm going to give LS by 2 minus LS by 2. And then assign thickness, height of the substrate. Say it is from 0 to some height of the patch, height of the substrate is assumed to be HS. Then in the bottom pane, you have to choose the material. So most of the materials have been already installed in the software. But if you want to design a new material, go for a new material and give the corresponding values of dielectric constant, loss tangent, etc. So suppose if you want a gene substrate in the applications of wireless body area network, then you have to define your own material. Otherwise, if for this particular planar ultra wideband antenna, the material which is already available in the load section I have to use, click on load from material library, and then it asks you what type of material you want. Just type on what material, FR4. So take FR4 lossy and click on. If you want another type of material like Rosers RT duroid, then click on Rosers. And in the Rosers, you have various types are there. So identify what you require according to your application that you need to select. So for this, I would like to select FR4, then click on load, click on OK. So then it is asking immediately, what about the value you need to provide initially starting the design? Say, I'm going to provide, say, 12, 24, and LS, say 30. Click on OK. And HS 1.6. Click on OK. So now whatever the component you have been created, that is to be available in the navigation tree under component 1 substrate. But as I already performed all these optimization process of the substrate, patch structure, and ground structure, and for the convenience of the researchers who is initiated to learn about CST, I would like to take those dimensions directly to avoid confusion. So I would like to take substrate here. What about X minimum? So for the designed antenna, what about width of the FR4 substrate is 24? It is to be equally distributed along y-axis, so minus 12 to 12, so it is minus 12. I'm going to take directly instead of parametric analysis, because that is what is the procedure I have been followed in the earlier case, that is parametric analysis to go for LS a different value, WS a different value, HP a different value. But it is already optimized antenna, so that I'm going for taking all those values directly here. This is minus 12 to 12, X minimum and X max, and Y minimum and Y max is to be minus 15 and 15. Then Z minimum, Z maximum, this is minus 1.6. 0 I have been taken. Either you have taken from 0 to 1.6. So what is my consideration in this case is, I'm going to take FR4 substrate with a height of 1.6. Either you can start that substrate from minus 1.6 to 0 or 0 to 1.6. It is your choice. So right now, FR4 lossy, click on preview and click on OK. So then it forms a substrate in the design window. So this is ranging from minus 1.6. Remember that value. And then I would like to go for design of microstrip line feed. So to design this microstrip line feed, I have chosen the dimensions. Width is minus 1.25 to 1.5. The length is from minus 15 to minus 1.5. And the patch thickness is 0.04 I have been taken. So again, go for brick, give appropriate name reflecting it. Then feed dimension, X direction minus 1.5 to plus 1.5. And then along Y direction, it is starting from bottom of the substrate, that is minus 15 to say minus 1.5. Then it starts from 0 to, because we have to place that patch structure on top of substrate, because the substrate is available from minus 1.6 to 0. So we need to keep that brick just on top of the corresponding substrate. So its minimum value is 0 and maximum value is 0.04, because I have to choose in the thickness of the patch is 0.04. And generally copper or gold material have been taken, and in this case copper annealed have been taken for the purpose of feed structure. Then click on view. So it is viewable there. Then click on OK. So for a clear view of this structure, three-dimensional rotation, I have to show you clearly. Further to view Q clearly, to eliminate this one. So this is the substrate you have designed, where it is from minus 12 to 12, minus 12 to 12 along X direction, and along Y direction it is from minus 15 to 15. And feed is from minus 1.5 to plus 1.5, and it is having a thickness of 0.04 only patch, whereas the substrate is having its thickness is 1.6. Again, remember that is substrate is assumed to be starts from minus 1.6. So the bottom coordinate, I would like to enlarge this portion so that it is clear. So the bottom portion is starts from minus 1.6 to 0. On top of this substrate, I have to place, on top of the substrate, I have to place this feed structure. So the bottom of this patch is 0 and it is having a thickness of 0.04. I think it is clear. Then I would like to go to design. The next step, design of rectangular patch. So first of all, I want to create that rectangular patch, this entire patch. From that designed rectangular patch, I have to notch some portions at the corners for the purpose of obtaining the required bandwidth. So come to here once again, design rectangular patch. Again, I'm going to take brick. So take brick, go to modeling, take a brick and give appropriate name to reflect it, a patch. So what about the component values have been taken for rectangular patch design? Optimized values are -9 to 9, -9 to 9. Then y dimensions -1.52, -1.52, minus 14.5, plus 14.5. Then again, because it is patch structure, so I have to combine this one with feed. So I have to take the same width as we have taken for the feed. What is this width? Is 0.04. The material is same. If you want, click on preview. So click on preview, got that structure there. So now on top of substrate, you have placed patch and feed. Now I would like to provide some notches at the bottom side for enhancement of bandwidth. So go for design of square shape 1. Again, I'm going to take a brick, but it is square shape of dimensions have been given like this. So again, go for brick, and defaultly it is having some name because I want to subtract these structures. I want to eliminate, I want to notch this portion and this portion from the design patch structure. I have to keep those names as it is, solid 1. Now go for the design values. Square shape 1, it is -9, -6, -9, -6. Then it is -1.5, 1.5, -1.5 and 1.5. Same thickness as patch and feed. So check preview is there. So this is the portion where the component is ready to align. So etched. So here this is the portion, so that I'm clicking on OK. So now check that component. So this is the component where you have designed a square type of structure. Now go for the second notch element, square type of notch element at the bottom side of the rectangular patch. Again, you go for take a brick, and then it is named with solid 2. Go for the coordinates. The coordinates are 6, 9. Then go for the y dimensions -1.5, 1.5. The thickness is similar. If the thickness is not to be chosen similar, when you are going to subtracting or adding or intersecting the structures which are defined, designed, feed patch, they will not be subtracted or they will not be added. So that these components which are placed on top of substrate, all these components must be having same type of thickness. So keep remember that point. So click on preview, you got that structure here. So click on OK. So what about solid 1 and solid 2 you got in this case are here they got. And this is the patch structure. And at the bottom side of the patch structure, I have designed those square type of patches. Now, what I need to do is to obtain this rectangular notched patch structure at the bottom side. Whatever the solid 1, solid 2, that is square shaped structures you have designed, you just select the component from which component you need to etch those components. First select the component. So patch, from patch, you need to eliminate those components so that use subtract operation which is available in the boolean. Then click on those particular structures where you need to notch. So I'm going to notch these two, so that I have selected these two and click on enter. Now you got the structure is like this. So this is the notched rectangular patch structure. This is the designed structure where I have shown for my proposed antenna. Now, so you have designed substrate, you have designed feed, and you have designed patch. What else the remaining is you need to design ground structure. So what about ground? So I just observe back view. this is the ground structure where you need to design right now. So what I have been followed to obtain this structure is, first I designed one rectangular type of defected ground structure up to here. Then I took two bevels at both ends with the help of an operation which is extrude. So how we can perform extrude operation on this rectangular defected ground structure, I would like to show you right now. So go back. So my aim is right now to design that defected ground structure. For that purpose, you can go back, design DGS. For this, I have to choose once again brick of dimensions like this. So choose brick, give a proper name for reflecting the object. So it is the ground. Then define those values, -12 to 12. This is feet of the width, width of the ground plane, and then length is -15 to -2.7, -15 to -2.75, and then where we need to place this component. This is important. So where we need to place this component is, we'll just like to show you that design structure so that it is very clear to you. As I said you, this one, yellow color one is substrate, and this red color one is a patch structure. So this is a patch, red one is patch, yellow one is substrate, and at the bottom side, yes, at this portion, I will highlight that portion. So that green one, which is nothing but ground plane. So I need to keep the ground plane below of the substrate. Just remember once, recall once what I had explained in the previous. So I have taken substrate from -1.6 to 0. Patch is to be taken from 0 to 0.04. Now the ground plane is to be taken below of it. So with a thickness of 0.1, I would like to take, so that what about the top point of this ground plane is nothing but bottom of the substrate. So what about bottom of the substrate? What about bottom of the substrate is -1.6. So what about Z minimum is -1.6, and I'm going to take the width of that ground plane as 0.1. So what about Z maximum value is, so it is going in the negative direction, so that add -0.1 to the Z minimum. So it is -1.6 minus 0.1, which is -1.7. And we need to take again the copper material for the purpose of ground plane also. So now you have to check and click on it. Okay. So this is front portion, and this is backside portion. So on substrate, a ground plane is to be deposited, and this is about feed and patch. So from top side and from the bottom side. So the design of substrate, ground plane, and patch structure are over. So it completes your design of an antenna. Right now, for the purpose of applying waveguide port, so we need to apply some amount of source to the microstrip feed line, and that should be applied to the edge of this microstrip feed line. For this purpose, I'm going to rotate that structure to obtain the face of the feed structure. Then you are going to apply that waveguide port to that feed structure. So for this purpose, because I'm going to apply waveguide port to this face, pick, you have an option is there, pick face, and then where you need to apply go there, double click on that structure. It will give a dotted line of portion like that. Then go into the simulation. There you have a portion is waveguide port. So click on that waveguide port. Then it is asking about the coordinates. So I shown you already the case of design specifications of microstrip patch antenna. What about the waveguide port dimensions are x minimum, x maximum, z minimum, z maximum. We need to apply, and those values are depending upon the width of the feed width and height of the patch, so that I'm going to apply those dimensions like this. So what about formula I had highlighted in the morning session PPT is 3 times to half of the half of the width of the feed. So what about width of feed right now in this structure is, I gave you already. So feed, what about feed is minus 1.5 to 1.5. So minus 1.25 to 1.5, it is 3. Half of that value is 1.5. So 3 times to that value. So what about that value right now is 3 into 1.5, where it is 4.5. Then here also x maximum 4.5, and then choose Z minimum. So what about this value I had specified there is, it is height of the patch plus 2 times 2 height of the, height of the substrate plus 2 times 2 height of the patch. In the design, what about height of the substrate I have been taken is, the height of the substrate is to be taken as 1.6. So that 1.6 plus 2 times 2 height of the patch. So what about height of the patch is, our microstrip line feed is 0.04. So 2 times 2 0.04, which is 0.08. So 1.6 plus 2 times 2 0.04, which is 1.68. So I can keep 1.68 here, and then go for Z maximum. In this Z maximum, it is 4 times to uh, 4 times to the value of height of the substrate. So what about height of the substrate is, it is 1.6. So that 1.6 into 4, which is 6.4. Then click on preview and then go for OK. Click on OK. Yes, this is the feed structure where you have applied to the microstrip feed line to match with 50 ohms to the antenna. So I'm going to provide impedance matching of 50 ohms with the help of this waveguide port to the antenna to avoid impedance mismatch. Now, if you want to have to change the structure colors as your wish by simply, say for example, feed the design, I have chosen feed patch as red color. So there you have an option is there. Choose the components feed patch, assign material color. You have red color. If you want, you have to choose it. So you got that red color, and then go for a substrate. So in the design antenna, I'm going to use yellow color. So go for yellow color, click on OK. Come back to the back side, ground plane. So where I have shown green color, so represent green color. So this is the designed antenna. Now, what you need to provide additionally is, this is a very important operation to perform on various types of structures, is the next one. You need to apply extrude. So I'm going to explain how to apply that extrude shape to obtain bevels at both ends of the ground structure, which you have designed earlier. So for this structure, for the design structure, I'm going to get bevels at both ends to achieve the required ultra-wide bandwidth. For this purpose, in the design, in the modeling, once again, go for the modeling. There you have extrude shape is there. Click on extrude, then click on escape. It will ask you the component values. there because it is already optimized antenna chosen already. So what about Z minimum in this case for the extrude is where you have started that defected ground structure is minus 1.6. From there, it is not asking Z max. Keep remember all of you, it is not asking Z max. It is asking about height value. So that extrude height, how much height you need is which is similar to the height of the defected ground plane structure. So what about defected ground plane structure height we have taken there is 0.1 and it is needed to penetrate in the negative direction, so that I would like to take minus 0.1 minus 0.1. So I took height is minus 0.1 and Z minimum is minus 1.6. And then later on, it is asking about that cursor coordinate values. So X values. So for the designed antenna, for the optimized antenna, the values are minus 12. And then you have minus 6, minus 12. So minus 6, minus 12, minus 12. Come to the y direction. The values are minus 2.75, minus 2.75, minus 2.75. Then you have minus 8, minus 8, minus 2.75. So review, there it is formed. There it is formed the bevel type of structure with the help of extrude. So if you have not properly chosen this Z minimum and height of extrude, it will not be subtracted from the defined defected ground structure. This is most important. Keep remember. So click on OK. Now what we need to do is define another structure. So what is the second extrude is, this is shape 1. Go for once again extrude. There you have once again you can provide minus 1.6, minus 0.1 and come to x coordinates 12, 6, 12, 6, sorry 12. Then go for y coordinates minus 2.75, minus 2.75. There it is minus 8, minus 8, minus 2.75. You can preview. Yes, it is okay. Yeah, actually it is not subtracted because defaultly those shapes are also with yellow color, so that it is it seems to be combined with substrate. What we need to do right now is we have to subtract those two components from the ground. So you have these components are there. So we need to subtract these two components from the ground. For that purpose, again you go for subtraction operation in the Boolean. So ground I have chosen. From the ground I need to subtract solid 1 and solid 2. Then click on enter. Now it is subtracted. So the rectangular beveled defected ground structure is obtained, which is the proposed structure as I had designed to obtain the ultra wideband shown in the PPT. So it completes our design process. Now you have patches there, red color, substrate, and bottom side of it, ground plane. Now, what you need to do in the next step is, because our optimized antenna is completed, we go for simulate the designed antenna. So for this purpose, we're going for setup solver and run the simulation model. So the simulation we have setup solver is there. So it is asking what type of mesh type. Default it is hexahedral. So minus 40 accuracy. Ports, I designed only one port. So port 1. So defaultly port 1, mode 1. So it is click on start. So I don't want to wait for the results where we need to obtain for this one, because it took almost 5 minutes of time. So that I'm going for already simulated antenna here. So after getting simulation, after simulation is over for the designed antenna, so you got the navigation tree like this. So we have components. In the component section, ground patch, substrate, and here ports. In the port section, your defined port is available. So if you want, you have to check it once. This is port. Suppose if you are going to use MIMO antenna, in such a case, you got port number as 2, say second for the second antenna. It is 1 for the first antenna, 2 for second antenna, 3, 4 for third and fourth antennas respectively in the case of MIMO. Now, we are going to check the results, the one-dimensional results. And in these one-dimensional results, port signals are available. So from the port, input signal, and this is output signal at the port. Then you have the most important parameter, S11 parameter. So we need to calculate the bandwidth by making use of this S11 parameter graph. In this case, the graph is obtained like this. Now we are going to check what about minus 10 dB values. So for that case, I'm going to take measured lines, which is kept at minus 10 dB line, one at lower position to identify lower cutoff frequency, and another one at higher cutoff frequency location. So it is typically 2.96 to 13.18 minus 10 dB bandwidth is achieved for the designed antenna. So this is about S11 parameter. And if you want to check what about the reference impedance, is that reference impedance is approximately 50. It is closer to 50. So we have provided better impedance matching by providing an appropriate coordinates to the waveguide port. So as we get approximately 50 ohms of impedance, so the antenna will radiate more effectively. Then go for next parameter, efficiency. You have radiation efficiency. Here the efficiency is in terms of decibels. Actually, while writing research papers, we have represented in terms of linear parameter. So multiply this value with 100, which gives you a percentage of efficiency. So we got that efficiency. What about the peak value of efficiency for the designed antenna? We got in this case is 98.5%. Thus, we can obtain radiation efficiency and total efficiency. Then VSWR plot is there. The value of minus 10 dB representing in case of S parameter reflects the value of 2 for VSWR. So whatever the value of VSWR equal to 2, there you can put the cursors and check what is the bandwidth from VSWR plot. So from this plot, this is a 2.9 to say 13.1. We got as in the similar case of your S parameter plot. Then go for Z matrix, because in some of the reviews I got plot the Z parameter plot also. So this is Z parameter plot, and they should ask clearly, specifically, what about real impedance and what about imaginary impedance of the designed antenna. So for this case, you have to check real, imaginary. If you want both in a single graph, go for real, imaginary in a single graph like this. So summation of these two, which gives you the value typically approximately around 51 ohms, as I had shown previously the reference impedance plot. Next, coming to, these are all one-dimensional plots. Coming to two-dimensional or three-dimensional plots, here surface currents have been obtained in the H field. So these surface currents defaultly have been taken. If you want, you have to obtain those surface currents at the defined frequencies. Say, I would like to show you one surface current plot here. So I would like to animate the fields. Animate now to clear view. If you want plot properties, there you have to provide for the clear view of the antenna. So I'm going to reduce. So these are the surface currents distribution over the antenna. You have to check the direction of those surface currents. Suppose if it is antenna is available with notched elements, then it is very clearly observed that at notched portion over the patch and the notched element, the surface currents are in opposite direction. Because it is only ultra wideband antenna, we cannot observe such type of surface current variations on the patch. Now come to far field. There we have to observe. Yeah, this is far field broadband. You have two plots are there. Now this is phi equal to 90. In the plot I shown you, I told you that phi equal to 90 gives you H plane and phi equal to 0 gives you E plane coordinates. So in far field, suppose if I want E plane radiation pattern, click on it, right click, then far field properties is there. Change this phi value as 0 and click on OK so that you got that radiation pattern at phi equal to 0 degrees, which representing your E plane. At phi equal to 90 degrees, it is representing your H plane. And suppose if you want to get these frequency components, these radiation patterns, at the resonant frequency of your designed antenna. So we have to check where the resonant frequencies are available for our designed antenna. Go there in S parameters. Say most negative is this one. So this is resonant frequency. There just observe what about resonant frequency value. So it is 12.296 gigahertz is the resonant frequency. So at this frequency, suppose if you want to know what about radiation pattern, there you just go and change that frequency value as 12.29. Already it is there. So for 12.29 itself, the radiation pattern is available. Suppose if you want to go for another radiation, another resonant frequency, say for example, this one, again go for know about the exact value of resonant frequency 3.45. So at 3.45, at 3.45, you can apply, yeah, change the frequency 3.45, click on OK. You got, because phi equal to 90 degrees, H plane radiation pattern. So thus we can observe the radiation patterns. And then you have one-dimensional results are there. So maximum gain over frequency. To observe this maximum gain over frequency, we need to go for template-based post-processing or result templates in the new software. So for this purpose, I would like to show you, because the time is already over, I would like to show you. Go for post-processing. For obtaining gain plot, go for post-processing. Go to result templates, because I have already simulated that one. I just want to delete that one and we'll show you how to obtain that plot. Now in the tables, you don't have any gain plot. Now go for post processing, which I had already shown you in your PPT. So select far field and antenna properties, then check far field result, which I had shown earlier, maximum gain over frequency, click on OK, then click on evaluate. Yeah, this is the gain plot for the design ultra wideband antenna, where it is typically ranging in between say 2.5 approximately to the maximum value of 4.42 over the ultra wideband range frequency of 3.1 to 10.6 gigahertz. So in between 3.1 to 10.6 gigahertz, it can show a maximum gain of 4.42 dBis at 7.99 gigahertz. Means the variation of the gain is in between 2.5 to 4.4. Means it is 2.4 to 2.5 to 4.4 means it is less than 2 approximately. So stable gain requirement is an important parameter for an ultra wideband antenna. Say you can notice it clearly by changing the view. Say this is from 0, this is 10. So the variation is very small, which is noticed from entire operating band frequency of ultra wideband 3.1 to 10.6 gigahertz. So with this single antenna ultra wideband antenna design is completed. And then I'm going to discuss about design of rectangular microstrip UWB antenna in side-by-side configuration to obtain time domain characteristics such as group delay and phase response. So to obtain that one, because time is already over, I would like to show you already simulated side-by-side and face-to-face structures of the antenna. Yes. So here, this is the first antenna and this is second antenna. So for the first antenna, ground patch substrate are these. What I have done to obtain this second antenna is just going through simulation. There you have transform option is there, translate. So I'm going to require another structure of the same antenna, so that I'm going to copy that structure with a repetition factor of 1. Say for example, if you require 2, you can provide 2 here. If you require 4, you can provide 4 there. So I'm required another one, so I can provide repetition factor as 1 and maintain some distance. Typically, for studying about time domain analysis, the distance between two adjacent antennas is typically taken to be 30 mm, sorry, 300 mm or 500 mm, like 30 centimeters or 50 centimeters, so that choose the distance in between those two antennas. Next direction is say 300 mm, because we chosen the dimension default values as mm's. So that choose there and then click on OK, then it forms the second structure. So ground 1, patch 1, substrate 1. Now what about the two components, two antenna structures you have, or this is antenna 1 and this is antenna 2. Now they have been placed in side by side arrangement with a distance of 300 millimeters of distance. The same you can perform to obtain side, opposite face-to-face type of structures. So here also same, ground patch substrate is the first antenna structure, ground underscore 1, patch underscore 1, substrate underscore 1 is the second antenna structure. So keep them the distance of some 300 mm or 500 mm. Now we can go for simulation. Start the simulation, same procedure. So where you have performed earlier for single antenna, go for setup solver. So we have two ports are there. I would like to show you the port of second one also. So in the port section, you have port 1, port 2. Two are available. So port 1 with the number 1 and the port 2 with number 2. So port 1, port 2. So you got S21 parameter, S12 parameter, S11, S22 like that. So here again come to the structure default view. Yeah, port 1, port 2. Now we have to observe the pattern, the port signals, input port signal output at port 1 signal, for output signal at port 2. And then you have S parameters once again. So S11 parameter, which is obtained for the single antenna case exactly. So this is the graph where it is obtained for single antenna. So single antenna S11, now it is in side-by-side configuration S11. Now it is S21, where it is noticed to be less than minus 30 dB over entire frequencies. More clearly, for the operating band of frequencies of UWB from 3.1 to 10.6, it is more less than minus 35 dB. I told you S21, which is less than minus 30 dB, confines the linear phase. Whenever it is linear phase, you got a minimum phase pulse error response. So in this case, we got that value less than minus 35 dB. Again, you have reference impedance. You have port 1 reference impedance, port 2 reference impedance are there. And then you can go for efficiencies, radiation efficiency of those antennas. Then go for VSWR plot, which I had discussed in the single antenna case similarly. Now you came across two-dimensional results. Surface currents are same, far field results same, radiation pattern. Now our intention is, what about group delay? So this is the plot of group delay. So verify this group delay, where this group delay, just I want to check what about the minimum value and maximum value. So what about the minimum value here? You have achieved is 1.19 nanoseconds. And what about maximum value you have achieved is, it is outside range actually, because operating frequency is from 3. So at 3 maybe 1.24. So 1.24 and another one is 1.29, where the variation is less than 0.04. That is the reason why we have to say that the group delay is almost flat to provide a minimum amount of pulse distortion from the designed ultra wideband antenna. So this is about group delay. If you want, I want to show you how to obtain that group delay. Yes, go for processing. Go to the result templates, far field antenna properties. There you have not far field result. There you have some other option. This is not far field antenna properties. Here you have filter analysis. There you have group delay. Yes, from port 2 to port 1 or port 1 to port 2, you can obtain the group delay. Say I have to evaluate that value. So I got the same group delay response here. So this is about group delay. And then to notice about the phase response, there you have in one-dimensional results, you have S21 parameter is there. There you can go, and in the result pane, in the one-dimensional plot pane, you have phase is there. So click on the phase. Yeah. Now verify these phase plot. It is very clear. It is a linear manner. So if suppose you have designed one ultra wideband antenna with band notch element, there is some amount of fluctuations have been taken place at that particular band notch frequency, where it is not to be noticed because we have designed ultra wideband antenna. So this is representing linear type of phase response. So S21 value of less than minus 35 dB, group delay variations of less than 1 nanosecond confirms this phase response, which confirms the designed ultra wideband antenna produces minimum amount of pulse distortion. Similarly, the same thing is to be noticed in the case of face-to-face configuration also. I just want to show you those plots S11, which is similar for single antenna when the two antennas are separated in face-to-face arrangement. And there is some deviation in the S21 parameter because we have placed in this case the antennas not side by side, we have to place them in face to face. And then we have to verify the group delay. The group delay in face to face configuration, it is also a very flat where it is conforming less than 1 nanosecond variation in the group delay. And then we can observe the phase response. This is what is the phase response, a linear type of phase response. Yeah, actually I want to show you our remaining two designs also because time is not permit, already 20 minutes over exceeded. Sir? Hello, sir.
Yeah, yes, sir.
Sir, shall I continue? Shall I continue or what about from audience?
Yeah, I think how much time it will take, sir?
It took more time, sir. It took almost 1 hour to discuss about another two structures.
Oh,
That is
okay,
the reason why I'm taking for permission from coordinators. Because it is complicated, somewhat complicated. Just ask them, the participants, any queries, sir.
It's very interesting. If you can carry on, and if the organizers can allow us to carry on for some more time.
Yeah, any participant, there is from participant response.
So we request organizers to allow you to continue.
For organizers, there is no issue, sir. So it is completely depending on the participants' interest.
Madam.
And as a participant, I am interested to request sir to continue.
Yeah, actually,
Yes,
it is
we are ready to
12:53.
listen,
Shall we take a break?
We are ready to listen. No issues.
Sir, okay, madam, I am requesting you, madam, coordinator.
Madam, shall you continue after 1 hour so that we'll complete the lunch and we'll get back to the session?
Yeah, it is better.
Yeah, because I had already explained all the details, madam, I am requesting you, the coordinators and HODs. It took 15 minutes of time to complete just the structure details because all the results I had explained very clearly. What about the remaining I have to explain is how these obtained structures and what are the different operations have been performed to obtain these structures, past structures, either this fan shaped type of structure or elliptical type of shape structure. I just want to discuss about those, how to obtain within 15 minutes, if you permit.
Yes, sir. Please.
Shall I, okay, madam? Shall I continue?
Yes, sir.
Thank you, madam. Thank you. Yes. So remaining all the feed structure. The feed structure. So in the feed structure, you have rectangular microstrip line feed is used. Then you have fan lipo like type of structure is there. And in the ground side, the same type of structure, because I don't want to explain once again how this structure is obtained clearly as I had explained in the previous case. But I would like to take you a new design, a new project, and to explain how this patch structure is obtained within 5 minutes. Yes, for this purpose, actually I have the structure is also there, how it is obtained. Yes. So for if any urgency is there, I had simulated, I had designed this antenna also for the purpose of participants to explain in a quick manner. This is a structure. So how it is obtained is very simple. So first I have taken one cylinder where the cylinder having this outer radius, inner radius. Yeah. So outer radius I have to 8, inner radius is 7.5, and the center of the cylinder is to be chosen to be origin, x center and y center 0, 0, and z minimum maximum which are 0.02. If you want, I would like to design the same by taking one new template. So I have taken one new template here. So I will go through quick manner because time is already taken more. Yes. So knowing that we avoid lineage. So I'm going to modeling. Then there you have, because I have shown brick extrude only till now. So go for cylinder or elliptical cylinder. You have that option is also there. So we have in the next design I have shown with elliptical cylinders. So cylinder, circular cylinder, and click on it, escape, and go for coordinates. Solid 1, as I said, it is 8 is the outer radius, 7.5 is the inner radius, making center of the structure is 0, 0, say that is having 0.04. And again, because this is a patch structure, I'm going for copper. So copper annealed, click on load, and then preview. Yes, it is